last week, I guess, if I remember correctly, we did some discrete systems here. And then we went into the Z transform. But we did that for the first order system, basically, and then we switched to the second order system. And we just did a little bit, so let's pick up on that, alright? So, if you have, let's say, what kind of system? A torsional system, let's say. Yeah, torsional is no mechanical, linear system, not torsional. Torsional will be in the frequency. So what we have is a spring and a mass. So when we apply a force to it, there are two resistive forces, the force in the spring, the force in the mass. So the extension becomes equal to mx dot plus dx dot. And then if you take the Laplace transform of this, we get f external of s equals s squared x of s plus b s x of s. CG şu arkadaşa elden ele geçiyor. So notice that I included this should be done. That's an example. I didn't put a spring in there. You're going to see why in a second. So this becomes ns squared plus es times x of s equals to that f external of s, and then we have the input-output relationship, which is the transfer function of the system as x of s, the output, divided by the input, equals 1 over ns squared plus ds. Okay? So I can express this as, taking this on the other side, f external of s. So what we basically have is I'm entering, forcing the system or exciting the system, excitation force, giving energy to the system, and the system is a second order system. Alright? And what I'm getting is x of s. Okay? But I cannot, as you can see, this is an open loop. Alright? There is no feedback. I have no control over what I want x to be when I give it the system x, f. So I close the loop so that I can get information about the system. Alright, and then what I do is I have amplifiers. So I can control the input to the system. Let's call it K. Alright, an amplifier you take in a digital system. You know what an amplifier is, right? Operational amplifier. Right? So you can just gain the system and you do that. So what happens is here. So we have the closed system then, and the transform equation becomes this K comes next to this. Well, you don't even have to. Yeah, you just do this first. K here by amplifying the force, and then afterwards, when you close the system, what you get is, this is minus, this is plus, Kf minus x times 1 over m s squared plus ds is equal to x itself. And then you take that out, of course, Kf, you can multiply x with this, and s squared plus ds, so that we don't have to mess with the system. Kf is equal to, Kf is equal to, we probably have to put the k here. Yeah. Well, let's try. Kf equals, x goes on the other side, so we have 1 plus, that's ms squared plus bs plus 1. Yeah, we don't want to put the k, we want to put the k here to amplify the edit. Let's do it like that. Alright, so I take it back. This is your thing. And then you put a K here to amplify and close the loop. So the K comes here. F minus x times K, yeah, that's right. So you have K here. Good. Times x. And then x over f becomes k over ms squared plus ds plus k. That's better. So we put that here. So the closed loop transfer function of the system turns into f going into 1 over ms squared plus ds plus k. And comes now x. And is equal. Alright, is that okay? We put the k not as the amplification factor here, but here, which made all the difference. So what you're doing is you're getting the error, and then you're amplifying the error into the system. You should put a controller here, so that you work on the error to reduce the error. But in this way, the system is going to control itself anyways. So anyway, the transfer function of the system that I call G of S is k over ms squared plus ds plus k. What we do is divide everywhere by m. So I have k over n, I'm going to call this omega n squared by definition, divided by s squared plus d over n s plus omega n squared. So this is the canonical form of the second order system transfer function. Alright, can't be any simpler than that. If you start with an BKM system and then put the force on it, then you end up with 1 unit, which is not something that we like. The reason we don't like it is because, as you remember, T becomes, when you go to Laplace transform, becomes 1 of S, 1 over S, right? So, for that reason, if you multiply with T, it means that you're dividing with S. And when you multiply with time, then you integrate, right? Like F times dt, you integrate with time. Okay, so time integration. So when you try to see what the output of the system is going to be if you give a unit impulse, which is in that case f of s is going to be 1, as you remember. Alright, what is the impulse response of the system? And you remember that the impulse response of the system characterizes the system, because if you give delta of t to any linear time invariant system, you get the system itself, the impulse response, right? If you give the delta of n into a discrete system, you get the discrete system itself, right? That's why g of n that we use to describe the transfer function of the system is actually the unit response of the system. So the transfer function is the same thing as the unit response. Alright? Unit impulse system. You understand that, right? I mean, there's no complications. So when I give the unit impulse to the system, alright, then x is going to be this. And when time goes to infinity, which means that s goes to 0. Right? And if s goes to 0, then wn squared over wn squared, my output is 1. Right? So we normalize time, the unit, or the transfer function, so that the response to the unit, the steady state response to the unit impulse is 1. Alright. So after saying that, after having said that, let's look into that system and its response to various inputs. First of all, I want to see its roots. S squared plus d over n s plus omega n squared. The roots of the denominator. Those are, as you remember, the poles of the system and determine the dynamics of the system, how the system moves in response to a force. So determine the roots of this. The roots of the denominator of the transfer function are the poles of the system. And if the numerator also is also a polynomial in S, then its roots will be the zeros of the system, as you know from last week. So this actually is a all zero representation. We would like to say it in control. Zero pole representation of transfer functions, the roots of these polynomials. The denominator of the transfer function is called the characteristic equation. Okay. So the roots of the characteristic equation are called the poles of the system. Definition. So that you can put it in your mind in a strong way, because you will, as engineers, use this over and over again in your life if you want to invent this system. So in order to find the roots, we set the system, we set the characteristic polynomial, let's say. Equal to 0. And then its roots are going to be S1 and S2 are going to be 1 over 2 B over M, right? Plus or minus square root of B squared over M squared minus 4 omega N squared. Just high school algebra. Now the polynomial, the roots of the polynomial, we have that is minus b, right? That's minus b, right? So are situated in the S-plane at the point where this is minus 1 over 2b over m. On either side of this, situated here and here, the two poles, S1 and S2. Okay? And they are separated from that B by that square root of delta. This is going to be 1 over 2b and minus the minus over here, and 1 over 2b and plus here. So the minus and the plus are here. Well, what happens if this here is 0? If the delta is 0? That could happen if b squared over m squared is equal to 4 omega n squared. Alright? Then we call that situation the critical case. And we're going to see in a minute why that is the critical case. So let's equate it to b squared m squared minus 4 omega n squared equals to 0. And we have this equal to that. B squared. So b squared over m squared is equal to b over m is equal to 2 omega n. So b equals 2m omega n. And remember that b is the damping coefficient. So if the damping coefficient is strictly equal to this value, right, then we say that we have critical damping. And whatever the value of B is, the actual B, its ratio to the B critical, okay, which is of course B over 2m omega n. Right? We call this the damping ratio. and we call that zeta. Alright, that is the meaning of the physical parameter zeta. Okay? And it is critical because if zeta is equal to 1, which is that, equal to that, or if zeta is greater than 1, or if zeta is between 1 and 0, or if zeta is 0. That gives us 4 different cases. Right? That's going to determine the response of the system. And if zeta is over 1, we call it overdamped system. Okay? Damping means to slow down. And what is that B, the damper, slowing down here? It's slowing down the omega n. Alright? So what does that mean? It's slowing down the oscillations of the system. Okay? So if the system is overdamped, it means that there's no oscillations. The system does not oscillate. It is so damped, which means that the resisting force of the damper is so high that when I pull the system, it just goes and settles. Alright? It doesn't overboard and then oscillate. So therefore here there is no oscillations. So therefore the system is something like that. If I give 1 to the system goes. Okay? Never reaches 1 mathematically. But eventually it does reach, of course, because mathematics and physics are different because we have assumptions. Okay? But it reaches that 2% critical value, TSS. If it's 1, then the system is critically damped. Then the system has no oscillation. But the system is reaching this value in the shortest amount of time. Awesome. Okay? Quickest. No oscillation, but settling time is the quickest. That's critical damping. If it's overdamped, then it takes too long to settle. Okay? So if you want to have a system that you know has a mass and everything in it, but you don't want to oscillate, okay? But you want to settle in the shortest amount of time, then you choose your delta, your zeta equal to 1. And those are all design criteria. Okay, these are the choices that you make when you're designing your system. Depending on what either your customer requires, what he has or she has specified, customer specifications, or your design criteria yourself. Okay? If it's that between 0 and 1, then the system is under damped. Therefore, there's going to be oscillations. Now, don't get this wrong. Here, the system wants to oscillate, okay? But the damper doesn't let it, okay? There are oscillations. And they last a certain time and they damp off. And then, if zeta is 0, this is undamped case, then no, then infinite oscillations. And then we have this case. Alright, so, and the values of each one of these, for example, we have in engineering, we don't just say, I want oscillations or non-oscillations, I want this or that. We have very strict specifications when we are, like for example, the thing of Elon Musk's release, the thing comes down. It has to be so very precise. Okay? You cannot just be satisfied with I want my thing to oscillate or not oscillate. You want it to be like perfectly in place. Okay? So we have to specify, have more specification. For example, how much do we want this, what we call overshoot? This is 10%. Where do you want it to cross the thing? The one line. The line that it's supposed to slip down into. Two lines. Okay? When do you want it to cross the value where this is 0.5? This is TD. The customer is going to give you not one, not two, but very many specifications. How much do you want this to period of these oscillations to be? Okay. When do you want the settling time? All of these are mathematically determined from the roots of that equation. And then you apply the value of the delta to that, and you determine every single thing. Every single specification of the system. Alright, do you understand what I'm talking about? Is that clear? So these are design specifications. These all time domain. We are in the time domain. Okay? Design specifications. Some customers just want pure oscillations. They don't want any damping at all. Alright, so let's just go into that. And who's my timer? Do we have time?
20 minutes.
20 more minutes. Alright, kind of nice. So let's just keep going with that equation. So we have the characteristic polynomial, the closed loop characteristic polynomial. We close the loop, alright, and we obtain a transfer function, and the denominator of that transfer function is the characteristic polynomial. Since the loop is closed, it's the closed loop characteristic polynomial. Okay, so closed loop characteristic polynomial. S squared plus b over m s plus omega n squared. Now, b over m, what the hell is that? Well, we define zeta as 2 b over m as 2 omega n, and that is zeta is equal to this, so b over m is going to be equal to 2 n omega n going over here. Okay? So this is going to be s squared plus 2 zeta omega n s plus omega n squared equals 0. We are after the roots of that data. Okay? So now, as you can see, we fully parameterized. We use two parameters to simplify the equation and determine the omega n, the undamped natural frequency of this, undamped. The omega t, the damped natural frequency of the system, which we're going to define in a second as omega t equals omega n times square root of 1 minus zeta squared. Omega n, if zeta is 0, omega t turns into omega n. If zeta is 1, omega t is 0. If zeta is 1, omega t is 0. Okay? So that makes perfect sense to call it the damped frequency. Damped frequency. Sometimes if you calculate it wrong and your system collapses, we call it the damped frequency. So it very easily can turn into damped frequency, right? So be careful. One of the most important things, because it has K, M, and B in it. Everything is in there. Okay? Alright. And then the S1 and S2, omega n is the natural frequency. And zeta is the damping ratio. B is the damping coefficient. Okay. So by using these many parameters of the system, we express our design criteria, design specifications, time. And it's time domain because we're talking about the movement of the system x in time. That's the behavior of the system in time. So S1 and 2 are going to be equal to minus d over 2. 2 zeta omega n divided by 2 rho plus or minus 1 over 2 square root of g squared 4 zeta squared omega n squared minus 4 omega n squared. And then the 4's come out as 2, and we cancel this. Omega n's come out as omega n. And we're left with minus zeta omega n plus or minus omega n square root of zeta squared minus 1. This, if you remember, is a redundant parameter. You actually have defined all the values of the system using these two. Using these, not these two, but using the zeta and omega n. This is enough. Right? But you are not satisfied with it, you just want to see this to simplify, further simplify the equation. So this is a redundant parameter. But extremely useful parameter because it decides between destruction and survival. Right? Now I can create another redundant parameter. I can call this zeta omega n, the as sigma. Okay? Which is called, what is sigma called? What is sigma called? Old age eats away at the gray cells in the brain. Extinction factor, something like that. Extinction. In some coefficient. So basically what we have is minus sigma plus or minus omega n sigma squared minus 1. And then we're not happy with this still. Alright? We want to transfer this into a minus 1 deal to a complex number. Okay, so this complex number is going to come out as j squared log, and this is going to swap the things. Okay, so this is going to be equal to minus sigma plus or minus j omega n times 1 minus zeta squared, which we recognize as that for what we have is S1 and 2 is equal to sigma plus or minus j omega d, which is our familiar S thing. We've been talking about in the S plane, in the complex, when the Laplace plane, any point in vector can be identified by referring to its coordinates. So now sigma, which is the real part of S, and omega d, which is the imaginary part of S, can be plotted in the S plane as minus sigma, which is good, alright, because that's going to come to the top of the exponential, and it's going to make the whole thing go down. The whole thing go down. Okay? Otherwise, it's going to just go up and up and up. It's going to blow up the building. And of course, that's not good. So it's a negative sigma attenuation, yeah. Attenuation coefficient. That attenuation coefficient tells us how fast the thing attenuates. The oscillations attenuate. Okay? And then we have the j on the imaginary axis, omega d, which gives me one root here, S1, and its conjugate, minus omega d, another root here, S2. Okay? And then, interestingly, sigma being theta omega n, and this being omega d. Okay, so this is omega d, and this is theta omega n. Okay? So if I form the vector, which I can now because we talked about it and we are using the same language now. The vector S now, okay, its argument phi, or the complementary angle, let's call it theta, so that theta plus phi are equal to phi. Nothing but Greek. Look at that. As if we are in Thessalonica. Thessaloniki. Everything is Greek. Then somebody thought that was fun. Alright, it's alright. How much time, Jojo?
10 minutes.
Yeah, very well. And then we see that the tangent of that angle, tangent theta, is equal to omega d divided by the opposite and the adjacent zeta omega n. Okay? And what is omega d? Omega d is omega n 1 minus zeta squared divided by zeta omega n. So tan theta is equal to 1 minus zeta squared divided by zeta. So this angle, this line, okay, is going to give me the constant zeta things. I can change k. Now zeta 8, that's too much. And then, if you see that this thing, the length of this is S mag, right, is equal to this side omega d squared times this side omega d squared divided by omega d squared plus zeta squared omega n squared square root, right? By Thales, Pythagorean theorem. This is equal to the square root of this is equal to the square root of the sum of squares. And omega d squared is going to be omega n squared times 1 minus zeta squared plus zeta squared omega n squared, you take the square root of it. And this and that cancel, only this stays, omega n squared, and you take the square root, you get omega n. So that length is equal to omega n. Alright? So therefore, in the S domain, in the S plane, when you write your thing, the pole, this is equal to omega n squared. This angle is a function of zeta. Okay? This gives you the omega d anyways. So what you have is, if you want to change the behavior of your system, this gives you an excellent visual understanding of what you can do. The circle is constant omega n. Alright? The line is constant zeta. And this line here is constant omega d. So you say, I want to keep this constant omega d, alright? But I want to change my zeta. You go here. Okay? You make this change. Alright, you move your sigma from here to here in the design plane, and you get that much omega n and that much zeta. Okay, so it gives you a very extremely practical plane for playing around with your design. Okay? What is the condition? The condition is that you understand the mathematics. Alright, you don't understand the mathematics, forget it, little friend. Okay? Go sell some equipment that the German captive has produced. Be a salesperson. Don't stay in design and invention. Alright? Or become a technician and fix the things that have broken, that the German captive has invented. Alright? You don't need to be an engineer. But you have to understand the background, the underlying, the foundation of mathematics of the physical system in order to dominate the physical system. Right? Otherwise, the physical system is going to play with you. I see students down there in the control laboratories who are trying to, fly the drone, and the drone goes like this, and then like this, and then hits the wall and everything. The drone dances around them. Okay? Because their math is not strong. Their control, the understanding of control in the S domain of the behavior of the system is key to designing well-behaved system. Okay, so let's take one more step in this. We have the two roots of the thing as omega n squared divided by s squared plus 2 zeta omega n s plus omega n squared. Alright. So that the two roots are those. Okay, so I can write this as omega n squared divided by s plus s minus. Now, remember, if you have a polynomial, a s squared plus bs plus c, for example, it has two roots. So you write it as s minus s1, s minus s2, right? A second order polynomial is the product of two first order polynomials. A third order polynomial is the product of how many first order? Very nice. You deserve a break now. So that's what I'm going to do. S minus, what is that over there? Zeta minus zeta omega n plus j omega b times s minus minus zeta omega n minus j omega b. Alright, this and the closed loop characteristic polynomial can be expressed as this, open form, root by root, or in closed form. Alright, with the two roots together. Now, if you see here, s squared minus s2s minus s1s plus s1 s2 is also equal to that. Alright, so if I collect the s's, s squared minus s1 plus s2, s plus s1 s2, that also is equal to that. Okay, so the multiplication of the first root with the second root is going to give me this. And here, that. So I can write s1, s2, the roots of the polynomial, divided by s squared plus. Now what is that going to be? s1 plus s2. So it's going to be minus s1 plus s2 plus s1 s2. That also is the same. Okay? Alright, so we'll continue from there. Take a break now. You've been loaded. And we have all these parameters to calculate. So the f that we give into the system then, that we get the f, is going to be the unit step. Therefore, its Laplace transform is going to be what? 1 over s. So x of s is equal to this, the transfer function, times f external of s, which is 1 over s times omega n squared divided by s squared plus 2 zeta omega n s plus s omega n squared. Alright? So we found x in the s domain, which is good, but it doesn't help us because we all live and breathe in the time domain, so we have to take it back to the time domain and find the response in the time domain. In the s domain, we've already determined that the response is something like that. Right? The sigma is the left-hand plane, so we're good. The system is stable. But in the time domain, what does the response of the system look in terms that we can relate to in the physical world? So back to time domain. Now we can explain what is the time domain. So we have to take the inverse Laplace of this thing. Alright? And remember from your differential equations that probably we did in introduction to engineering classes, if you have a polynomial like this that you need to reverse to the time plane, what you do is you first express this as poles, okay? And then you separate it into fractions. We call that partial fraction solution. You remember that, right? The partial fraction solution. Because we don't know what the inverse of this is, we have to express it in terms that we can recognize as a inverse Laplace of something. So let's say the four cases that we have, theta is greater than 1, theta is equal to 1, theta is between 1 and 0, and theta is equal to 0. The first, the four cases, let's start with this. If theta is greater than 1, we have an overdamped system. We probably exaggerated our damper. Alright, so the system is like stiff. Okay? Let's express this as 1 over s omega n squared divided by s plus p1 whole 1 s plus whole 2, and that is equal to p1 times p2, as you know. Omega n squared is the product of the two poles. Remember that, right? It's been just 20 minutes. So zeta is greater than 1. And let's divide that later. This is going to be A over S plus B over S plus P1 plus C over S plus P2. Partial fraction solution. And we have to see what these constants are. The easy way to do this is the following. First of all, the root of this is s equals 0, right? The root of that is s equals minus p1, and the root here is s equals minus p2, right? So we do the following. We first start with a divided by s, and we assign s equals 0 to the value of s. This immediately blows up. 1 over s becomes infinity. So we close this. Right? It's a trick. Okay, so we close this, and we give s equals 0 to that. So what we have is equal to p1, p2 divided by 0, 0, p1, p2. 1. So A equals 1. That's a very neat trick that you can use to find these partial fraction solutions. Okay? Now we have this, and we're going to assign the value of s to minus p1. Okay? And since this is the root of s plus p1, we're going to close that. Okay, so to resolve this, we have 1 over s, this is gone, p1, p2 divided by s is minus p1 now, minus p1 plus p2. Follow that? Do you understand the trick? Whatever the solution of the denominators of the partial fractions, I assign the s to that. But if I say S equals minus P1, this becomes 0, so that thing will also, I cover that up. Okay? And I solve the rest for whatever is remaining. So here, if I close this, then minus P1 plus P2. P1 over P1 times P2 times 1 over S. A is 1. Right? Okay? Alright. So, and S is equal to minus P1. S is equal to minus P1. So this takes care of that. I have minus 1 times P2 over minus P1 plus P2. Oh, sorry. And that gives me P2 divided by P2 minus P1. So my D is equal to that. Anybody who's lost? I don't want to lose any of you, alright? So tell me if you don't understand right now at this point. It's alright, I can do it again, and again, and again. We have time. Everybody understands? Unbelievable. What a class. Okay. For C, then you tell me. What do I do here? S equals minus P2. Okay, so I have 1 over minus P2 for this. I cover this. Alright, I have P1, P2 divided by minus P2 plus P1. Okay? And P2 cancels P2. So I have P1 divided by minus, reverses the sign here. Let's say minus P2 minus P1. So that the two are equal to that. Okay? No?
The negative 1 shouldn't be P1 minus P2?
I put the minus up here.
Okay, and in all the options.
So I left this as is. P2 minus P1, so that these two are equal to each other.
And in the B1, where's that?
Here? Here?
Yes.
That reverses the sign here, P2 minus P1. Yes, it did. P2. Oh, it didn't. No, it did. That minus. Didn't it? P1 minus P2. P1 minus P2. Right, so that has to be minus, right? Let's check. And then B is minus P2, and this is plus P1. Is that right? That should be, because that's what my notes say. So we have A is equal to that, B is equal to minus P2 divided by P2 minus P1, and this is equal to P2 divided by P2 minus P1. Right, so now my thing turns into this thing, turns into what?
When you wrote B equals, the upper is P2. See? No, up. When you wrote B equals, it's P2. Minus P2.
Oh, okay, P2, thank you, and this is P1. So my transfer function times the input turns into x of s equals, now I'm going to write this in its equivalent form, 1 over s minus P2 divided by P2 minus P1 times 1 over s plus P1, and then plus P1 divided by P2 minus P1, 1 over s plus P2, hopefully. And then, this is a constant, that's a constant. This is a constant, that's a constant. So I have the Laplace minus 1 of the whole thing is going to be Laplace minus 1 of this, which is going to be 1, minus the constant P2 over P2 minus P1 times e to the minus P1t plus P1 times P2 minus P1 e to the minus P2t. So as you can see, if zeta is greater than 1, alright, we have no complex roots. Both roots are real. Okay? And if both roots are real, I don't have any WT, obviously. So I have 1 and 2. Both roots lying on the real axis. As predicted by the omega, by the value of zeta, no oscillations. Okay? Just the sum of two exponentials. Now let's call this x1 and let's call this x2 in order to plot, make things easier for us. Alright? So x1, I have to sum two exponentials, alright, which is not as easy as it looks, but it's doable. So x1 is going to be this multiplied by that, p2 minus p1, minus p2 divided by p2 minus p1, okay, e to the minus p1t. And the p2's cancel each other, so I have minus p1 divided by p2 minus p1 e to the minus p1t. Oh my god, this is so boring. x2 is equal to that, so I just write it as it is. x2 is equal to p1 divided by p2 minus p1 e to the minus p2t. As you can see, both exponentials are stable. Okay, the system is not going to blow. But what is the system going to do? Oh my God, what is the system going to do? So, x1 being equal to minus p1 divided by p2 minus p1 e to the minus p1t. Alright? When time is equal to 0, this is going to be 1. Okay? So my x at time is equal to 0, x1, is going to be something like p1 divided by p2 minus p1. The minus sign. It's going to be down here. Alright? Okay? At time equals 0. Yes.
What's for the P1 and P2?
What are P1 and P2? Those are the roots of the closed loop characteristic polynomial. So they are the poles of the system. That's why I call them P's. Okay? And previous hours, we decided these are actually S1 and S2. I switched the notation. These are S1 and S2. And remember that in the earlier case I said S1, S2 divided by S minus S1, S minus S2. Here I'm writing S plus P1, S plus P2. It doesn't make any difference because the sign is going to tell me anyways, alright? If I put the wrong sign in it, it's going to turn out to be minus, which it did. Okay, so those are the poles of the system. And the poles of the system are both on the real axis. Alright, this is P1, this is P2. Okay? Or this is P2, this is P1, this is P2. I don't know yet which one is bigger. Alright? Okay, so what a complicated deal. And as you can see from here, 1 minus some constant times 1 minus some constant times e to the minus p1t is my x1 or p1. Okay, that is going to be, this is what I'm going to plot it as a line, an exponential, okay, that is upper bounded, so it rises and stabilizes at some upper bound, because this is what 1 minus is. Okay? If it is just that, then it would be that. But if I have 1 minus, then this whole thing is subtracted from 1. Okay, so I have 1 here. And then as this grows, I take more and more out of the 1, so I go down. Alright? Oh. And the other one, x2, is p1 over p2 minus p1. p1 over p2 minus p1 times e to the minus p2t. So that starts from p1 here, p1 divided by p2 minus p1. This goes up and this goes down. Okay, this is bounded, and this is bounded by the lower asymptote. This is bounded by the higher asymptote. Okay? So the combination of these two, as you can see, is going to be something like this. It's going to start from 0, because this minus that is going to be 0, and time equals 0. Alright, this takes away that, so this takes away that, so I start from 0. Since I'm adding these two, okay? And then here, this is going to take over, so I'm going to have a curve that goes like this, and it's going to have a curvature, and it's going to come like that. So it's actually, since it has 2 exponentials on it, it is actually a second order system, which masquerades as a first order system, no oscillations, okay, but it has an inflection point here. Alright? And it depends on which one is the distant pole. Okay, if P2, for example, is too far from the origin, and remember that P2, the pole, is equal to 1 over tau, right? We haven't learned these for nothing. Tau means that it's a slow system, okay? So if P is large, okay, that means that tau is small, okay? Then this system is fast. This part is fast. So this inflection is going to disappear very close to the origin. Okay? The dynamics of the fast pole, this is the fast pole, and this is the slow pole. Don't forget these things, alright? just like from here. This is the slow system, this is the fast system. Okay? Tau is smaller than tau here. So 1 over tau is going to be bigger. So the pole is going to be faster. The more distant the pole from the origin, the faster the dynamics. Okay? So the dynamics are going to disappear very soon, and I'm going to see almost something like that. Almost imperceptible. Okay, but the bottom line is that the system has no oscillations. So if zeta is less than 1, then both poles are real, which means that they are on the real axis, which means that they don't have a omega d component, so therefore no oscillations. Yes,
Isn't
yes.
it be the zeta bigger than 1?
What?
It should be zeta bigger than 1? Isn't
Yeah,
it?
that's right. Very nice, you passed the test. Okay? Now, ladies and gentlemen, this was the easy part. Both poles are real. Now comes the real part. Well, actually, that's also easier. If zeta is equal to 1, okay? If zeta is equal to 1, now remember, mathematics, alright? This is your goal, this is where you start. You can go from here, you can go from here. If both paths are correct, you get to the same result. So you choose the easiest path in mathematics. So what's the easiest path for me to stay here, to start here? I say S1 and S2 are minus sigma plus or minus j omega n 1 minus zeta squared. Right? So if this is 1 and the complex part, the imaginary part disappears, so my roots are the same, 1 and the same, sigma. Alright? So I have again, very simple system with going to 1, but in a shorter time. In a shorter time than this. Okay, because this would go as fast as this, but the second pole slows it down. Okay, it loses some time here in the inflection. The inflection point. It's the second of the system. So if it loses some time, then the setting point is delayed. Okay? Follow this? How about the thing? Does the thing follow me?
Yes.
Alright, good. So zeta is equal to 1. We have double roots. Okay, because delta is 0. Yes, you wrote 1. What's wrong with me today? Huh? Testing. Constantly testing. So double roots, therefore no, again, omega d, no complex component. So therefore no oscillations. But the system reaches steady state faster. Because the second pole does not retard the first pole, yes?
I have a question. When you said that zeta is greater than 1, where did we use that in the definition?
Where did we use that?
That zeta is greater than 1. Where did
Greater
we-
than 1. Where did we use it? Well, we used it here. if zeta is greater than 1, okay, then this quantity becomes negative, and the negative thing comes out of here and cancels that. Alright? So we have minus sigma plus or minus omega n. Okay? Yeah, omega n. Alright. So we know that both poles are real. Okay? Now the real thing. This is where the fire hits the asphalt, and this is where the burning starts. So since I'm liable to make mistakes, I'm going to just follow my notes. I'm going to deal with errors. Now here, is it here? Sorry. Alright, okay. Now the third case, zeta is between 0 and 1, which we have it, which means you have an underdamped system, underdamped, okay? Not overdamped, not critically damped, underdamped. So we are going to have oscillations, okay? And again, we're looking at the unit step input response. So F external is equal to 1 over S, again. Unit step input. Now what does that mean, unit step input? I hope you remember that. It means that you have pulled the system and you kept it down. Okay? Now when you pull the system may pull you back up stronger, so it will go down, but the force is going to stay. Okay? Constant. So you're going to have something like this. Force is equal to 1. Okay, force. And then what is X going to be? Remember, the force is 1, X is also going to be 1, so it's going to be going up like this and fluctuating around 1. Why is the X going to be 1? Because we have normalized the system. If time goes to infinity, then S goes to 0, this disappears, that S disappears, omega n squared divided by omega n squared, we have 1. So the X is going to go to 1 if the force is 1. Okay? You can scale the force, and it's a linear system, so the output will also be scaled equally. Alright? So you call this F, then this is going to go to F. Okay? Just scale the system with a constant. The output is also scaled with a constant. But we like the normalization bit, so we call this 1, and we call that 1. So let's see how this thing appears in mathematical terms. Okay? Now x of s then is equal to 1 over s, omega n squared divided by s squared plus 2 zeta omega n s plus omega n squared. Even I can write this without any mistakes, okay? That's so simple as that. Alright? Remember, this is the canonical form of the second order, this transfer function. So now we have 1 over s and this a over s plus, let's call it p, because I know s squared plus 2 zeta omega n s plus omega n squared. Usually, when you have a second order system, a second order denominator here, what you do is you call it bs plus c. You give a first order system. Right? But in this case, there are many ways to reach the thing. So let's just call it B. So what we have here is going to be the following. On the bottom, okay, I'm going to have this times that. Okay. 10 minutes? Really? Why? Where's my girl?
She has to
left,
go.
huh?
She has to go.
She has to go. Oh, okay, thank you. 10 minutes, huh? That's cutting it too fast. But alright, we can do that. So, if I do the same trick here, like say S equals 0 to find A, and this goes, so A is equal to 1. Okay? So I have A is equal to 1, and then we have to deal with B now. So what we have is A S squared plus 2 zeta omega n S A plus A omega n squared plus BS. The two bottoms are equal and the two fractions are equal, therefore the tops have to be equal. So this has to be equal to, this bit has to be equal to omega n 0 squared, omega n squared, right? So I collect the A's. A S squared plus 2 zeta omega n S plus omega n squared. No, I don't do it. Sorry. That would be going back to the same thing. What we do then is we equate this to omega n 0, and since A is equal to 1, I can get rid of the A's. Okay? So S squared plus 2 zeta omega n S plus omega n squared is equal to omega n squared.
Plus BS.
Yes. What?
Plus BS on the left side.
What? BS plus BS. Omega n's go away. So BS, right? So we have BS equals minus S squared minus 2 zeta omega n S. BS. So BS cancels that and this. So B is equal to minus S minus 2 zeta omega n. And just like we said, this had to be BS plus C, right? But it gives you the same answer anyways. If I did this way or I did that way, it would give me the same answer. So B is equal to minus S plus 2 zeta omega n. Alright? So the equation turns into turns into 1 over S minus S plus 2 zeta omega n divided by S squared plus 2 zeta omega n S plus omega n squared. Beautiful, huh? So far, I mean, the beauty of mathematics, you see, it's painful, but it's a lot of fun. So, we have a term here that has this in it, which means that S has been shifted by that amount. you remember that, for example, delta of t, okay, gives you a delta that strikes at 0, but if delta t minus tau, you shift it by tau, remember? The same thing happens in the S domain. If you shift this, what?
In B, how it became plus 2 zeta Vn?
What?
In B,
B
how it became minus S plus 2
minus
zeta.
that.
Okay.
Thank you. That's why I put the minus
Okay,
here.
okay. Thank you.
So I see that the S is shifted here. And when the S is shifted, okay, remember what happens? 1 over S plus A. That gives me e to the minus AT. So I know that there's a component here coming from this that's going to give me this. Okay, because the S has been shifted. But the rule is that all of the S's have to be shifted like that if I want to apply that rule. Not just in the numerator, in the denominator also. So I have to manipulate the denominator. Okay? So that's the art of mathematics, and I strongly recommend that you do this all by yourselves without the help of that notes. Okay? Learn how to do it. Okay. X of S is equal to 1 over S minus S plus 2 zeta omega n. I recognize the 2 zeta omega n as my iteration factor, zeta omega n. Remember the sigma. Now on the bottom, I have to say that this S also has 2 zeta omega n next to it. But 2 zeta omega n, I don't like that. So what I'm going to do is zeta omega n plus zeta omega n. Okay, so that's 2 zeta omega n. So I have 1 S plus zeta omega n here. And I have an S squared, can't get rid of it. So I'm going to keep this S plus zeta omega n squared plus zeta omega n, but now the denominators are not the same thing. What is this? S squared plus 2 zeta omega n, S plus zeta squared omega n squared. Okay? But I only have 2 zeta omega n over there. So what I'm going to do then is I'm going to add or subtract minus zeta squared omega n squared from this. Minus zeta squared omega n squared. Okay? So if I open this, I get that. Okay? And then I have to have, I guess, another zeta omega n, right? Anyway, let's just continue at the top. So this I can take into parentheses S plus zeta omega n plus zeta omega n divided by S plus zeta omega n squared plus that minus that zeta squared omega n squared. Now is that correct? That brought in a 2 zeta omega n s And then this. Now let's just make sure that this comes from this. Okay? And then I have this comes from that, it takes care of s squared plus 2 sigma omega n s. Then I had a omega n squared from there, and then I have to get rid of this minus zeta squared omega n squared. So I guess this is just omega n squared. Zeta. This is that. So omega n squared minus that. So this takes care of that, leaves me this and that, which is the same thing as that. Oh. If you make something wrong, then time will tell. So now I have this and that in the same equation.
For this, time's up.
Time's up? Well, give me 2 more minutes. Thank you. You're so nice. So that is omega n squared 1 minus zeta squared. And if I do minus omega n squared, then I have zeta squared minus 1. Do I have a minus on the bottom?
I have a minus in the top. We have a minus in the top.
Do I have a minus here?
Yes,
Minus omega n. So this turned into omega d squared, but there's a minus here, which I don't like. There's got to be a minus here.
After 1 over s, there is minus and at the top.
Well, anyway, there's got to be a minus here. I think we had 2 omega n squared, and one of them had to be a result, so this has to be a minus. So then I do this is plus. Well, you'll do it in the home. I don't care. So what we end up with is s plus zeta omega n plus zeta omega n divided by s plus zeta omega n squared plus omega d. Alright, this really looks like
At least have these square with
omega d. This really looks like a cosine over here. If I had only this, so I'm going to split it in 2. S plus zeta omega n divided by s plus zeta omega n squared plus omega d squared. And then I have plus zeta omega n divided by the same s plus zeta omega n squared plus omega d squared. Really nice so far. Now if I can turn this into an omega d squared, then I have a cosine here and a sine here, which is perfect, exactly what I want. So what I do then is I multiply this with an omega d and divide it with omega d. So omega d times zeta omega n is going to be omega d times zeta omega n divided by omega d. zeta omega n. That's what I have here, and I divide that by omega d. So I'm trying to get an omega d squared, omega d up there. So instead of doing that, maybe we can do the opposite. Zeta omega n, omega d divided by omega d. And omega n is omega d divided by square root of 1 minus zeta squared. So if I put it in here, that's going to be equal to zeta omega d divided by 1 minus zeta squared. I took care of the omega n, so I have omega d divided by omega d. So I have zeta divided by square root of 1 minus zeta squared left here. And then I have omega d squared. What the hell do I do with this? Well, I don't do anything. Takes away that. Ah, beautiful. Yeah. Without knowing it, you saw that. So, what we have eventually is x more s equals to that. S plus zeta omega n divided by s plus zeta omega n squared plus omega d squared. Eating away from your time, I know, but we're going to take a longer break, I promise. Plus zeta divided by square root of 1 minus zeta squared. Omega d divided by s plus zeta omega n squared plus omega d squared. Beautiful.
You forgot one over s.
1 over?
Yes.
No, I didn't. I put it all in there. 1 over s.
The first one.
Oh, 1 minus. 1 over s. Yeah. Beautiful. So, the Laplace inverse is cosine omega dt multiplied with e to the minus zeta omega n t minus. This is plus zeta over square root of 1 minus zeta squared sine omega dt multiplied with e to the minus zeta omega n t. And this is what? Alright. So I take this in parentheses, 1 minus e to the minus zeta omega n t. In parentheses, cosine omega dt plus zeta over 1 minus zeta squared sine omega dt. Unbelievable. Excelente. Look at that. So we have a cosine and sine product, sum. Okay. And then we have an exponential attenuation, all subtracted from 1. So here I have the oscillations. Here I have the attenuation. And here I have the 1 minus 1. So it's going to go up here. And then settle down at 1. So we're going to do that in the next hour. But I'm sorry I messed up here a little bit, but it's a complicated thing and I'm old enough to forget these things. But you should practice it until you die. Okay? Until you solve everything without looking at your notes. Don't be like So who came last? You came last. I remember the color of your shirt. Alright, so this is your eraser. Now using trigonometric identities, which I tried to do but couldn't, that's alright, you can do it in your own work. This can be turned into an angle cosine theta times cosine omega dt plus sine theta sine omega dt. Okay, multiplied by some entity here, and this has to be divided by some entity. I don't know what it is, but it can be done, and I'm going to do it after class. So cos sine sine is sine omega dt plus theta. All right. So what we have here is t to the minus theta omega and t minus 1.
Cos değil.
Cos
Farklı olunca kos eksi oluyor zaten.
eksili olunca sin cos olur. Okey, canlı sağ olsun.
Yok
Eksi.
yok söyleyeceğim şey. Sinüsün çift şey açıldığında sinüs kosinüs diye oluyor. Kosinüs kosinüs olunca kosinüsün çift.
So sin cos ve sin cos mu? Ha? Söyleseniz o zaman çözerdik ya. Tamam, böyle yapacaktık. So this will be, because it has to be a sine. So what we're going to have is sine theta, cosine theta, right? Cosine. Then it's going to be sine. And this has to be plus. Already then. Already. Alright, excellent, excellent. So, what we have eventually is now, and the way to do this is imagine an angle theta. Okay? You have this clue here. So this here has to be the cosine theta. Okay? Cosine means this theta, this divided by that, right? So zeta is this square root of 1 minus zeta squared. Well, if zeta is this, then this is smaller than this. But anyway, something like that. Okay, so if you move around from this idea, you can transfer this into that form. Alright? That's really not the purpose of this class, and I should have, remembered it, but I don't, so hey, kill me, alright? So anyway, this has a sign, which means that we're starting from here, a sign from 0. Okay? But it's a 1 minus sign, so we have to subtract the sign from 1. Okay? So 1 minus this, we're going to have to start from here, and then we turn it into a sign now, like that. And then on top of it, we are going to have a exponential decay. Alright? So that we're going to eventually end up at this. So the combination of the two is going to be rise, oscillation, and dampening. And the settling value is going to be 1. Right, this is going to be x of t now. And this is going to be t. Alright, and the description of the system is going to have this value here, which we're going to call percent overshoot. Okay? The time at the peak the time where it rises to 0, rise time, and then the time where it rises to half of the maximum. And then we're going to have the damped oscillation frequency here, and then the settling time here. So all these have to be calculated. And then of course, to calculate the peak and the time at the rise to the peak can only be calculated by taking the derivative of this with respect to time. To calculate the maximum, you have to take the derivative of this set equal to 0, you remember from your calculus. So, it's dot of t. If you do that calculation, this is going to drop, of course, to 1. And then you have to have the derivative of this times this, plus this times the derivative of this. Okay? Chain rule. So, of course, I'm fired on making mistakes. What you have is the following. Zeta squared divided by 1 minus zeta squared plus square root of 1 minus zeta squared times sine omega t. Okay? If you set this equal to 0, then this you don't care about because it does or doesn't become 0. We don't. It probably never becomes 0. This becomes 0 if zeta is 1. This becomes 0 if zeta is 0. So the two don't equal 0 at the same time. But this can be equal to 0. And when is sine equal to 0 on the unit circle? This and that have 0 signs. So this is 0 angle, and this is pi. And then this is 2 pi, and then this is 3 pi. Alright, you go around and around and around. So you have 0, 1, 2, 3, 4, 5, on and on like that. So if this is equal to sine omega dt equal to n pi, okay, an integer times pi, then the sine has to be equal to 0. Okay? So therefore, sine omega t equal to 0. So if this is equal to that, then sine is equal to 0, I should say. Therefore, time is equal to n times pi divided by omega d. Okay? And the first time this is equal to that is when n equals to 1. So this peak corresponds to pi over omega d. The second peak corresponds to 2 pi over omega d. The third peak, 3 pi over omega d. And so on. Okay? You follow this logic? This cannot be equal to 0 for all t. Therefore, in order to make the derivative 0 so that we can calculate t, we have to take this term and equate it to 0. And sine can only be equal to if it's to 0 if its argument is equal to an integer multiple of pi. Okay? So we have n pi over omega t gives us the time to the peak. Beautiful, huh? Does anybody understand? You do? Unbelievable. Alright, this is what we're going to do actually. You have to learn how to do this kind of logic when we're doing the frequency domain. Alright, we always find out in the frequency domain when something is equal to 0, something is equal to p, and everything like that by doing this type of logic. Alright? any sign is equal to 0 if the argument is equal to pi n. Alright? Any sign, omega dt for example, is going to be equal to 1 by the same logic, okay, on the unit circle, when the argument is a integer multiple of pi over 2. Right? Not that we're going to need this here, but the same argument applies to this. Okay, then sine is equal to plus or minus 1. Okay? If it's an odd multiple of this, then it's going to equal to plus 1. Alright? So if we say omega t over t is equal to 2n plus 1 pi over 2. This has to be odd always. Whatever n is, this thing is odd. You follow that? Well, I hope you do. Those who follow this, do this. Nobody? You do? You do? Those who follow, don't follow it. Okay. Just as an introduction to frequency dynamics, we're going to go in probably 2 weeks from now. Now look. On the unit circle, right, this is equal to 1. Any angle, theta, okay? Cosine of theta is this divided by that, right? This divided by this, oh my God, that's what I was doing here. It has to be this divided by that. That's the cosine, yeah. Well, that's anyway. So, and the sine is this. So when the angle is 0, its cosine is 1. Its cosine is 1. Its sine is 0. When the angle turns around and becomes pi, okay, the sine is again 0. Follow that? When it turns around and becomes 2 pi, the sine is again 0. So whatever the angle is, sine theta, okay, is equal to 0 if and only if theta is equal to some multiple, integer multiple of pi. Get that? Alright, what is the argument of sine here? It's omega dt. So I apply it to that. Omega dt is equal to n pi. So I get t from t is equal n times pi over omega d. Alright? So I want the sine to be 0 because I want to maximize this. So its derivative is 0. And I cannot take this to 0. So this has to be 0. And therefore, the argument has to be a multiple of this. So therefore, the t time has to be that every time an integer multiplies this entity, the function peaks. So the first time it does, that's the maximum height. Is that clear enough? By the same token I was explaining here, alright, for the cosine to be 0, for that angle, okay, the angle has to be 90 degrees. Because cosine theta is 0 if and only if, okay, the argument theta is a multiple of pi over 2. Here 1 times pi over 2, 2 times pi over 2, 3 times pi over 2, and so on. Okay? But this has to be an integer multiple. Okay? It cannot be, for example, an odd multiple. This cannot be 2. If n equals 2, then I have pi, so cosine is minus 1. Okay, so I have to think about these things. And those are going to be extremely important when we're looking at the configuration of the frequency domain response of a function. So just keep that in mind. And if the thing peaks at that time, TP, then if I put TP here, okay, then it's going to be maximum. This is going to be maximum. So if I subtract that maximum from 1, I'm going to get 10%, right? And there are all sorts of calculations to do that. So I'm just going to give you the summary of this. The maximum at peak is equal to y at TP minus 1, y at TP minus 1. So I'm looking at this value here, the overshoot. And that's going to be equal to e to the minus pi zeta divided by 1 minus zeta squared. Right? So that is going to give me the amplitude. And you see that the maximum overshoot, this is we call overshoot. Right? We want to actually minimize this because we don't want the system to go and then settle down. We want this as smooth as possible. Okay? So, and it's a function of zeta. The higher zeta, the smaller this is because of that minus. Okay? And if you have zeta infinite, then this is going to be 0. So you're not going to have any overshoot. Okay? If zeta is greater than 1, okay, then this is going to go down, 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 all the way to 0. And then you can actually put that in your engineering design chart. It's a function of the zeta, this goes down like that. Okay? But this is such a smooth, slow curve that you can actually linearize it. And n becomes equal to 0.63 minus 0.84 zeta. The linearization approximation. So that is another tool for us to design a well-behaved system with a small overshoot. Okay? TSS, as always, is equal to 4 tau. And in our system, tau is equal to this attenuation factor here without time. Okay? So it's going to be 4 divided by zeta omega n. 4 tau. Okay? Since this is our pole on the real axis, inverse of it times 4 is going to be the attenuation factor. I'm sorry, not the attenuation factor, the steady state. So on and so forth. So what I wanted to do today then is to give you an idea about the behavior of the second order system, which is more realistic than a first order system, of course, because there's always mass involved. You cannot neglect the mass easily. Okay? And then you're going to have oscillations in your system because every system has a spring coefficient. Even that has a bending coefficient. Alright? If you bend it just tight enough, it will oscillate, but the damping is so high that it will not oscillate. But a more flexible system is of course going to oscillate with its damping. Anyway, so you understand that in the time domain and in the x domain, design the system as you want. So this is going to give you constant zetas. This is going to give you constant omega n's, and this is going to give you constant omega d's. So you can play around with your system as you want. How much time do we have?
12 minutes.
12. 11. 10. Any 10? Alright, excellent. So let's just quickly go over the second order discrete systems now. Okay, as you remember, the discrete system was xn going into yn. What that was the delay box, and then that was the core, and then we were adding the two. Remember, as opposed to the continuous time system, where you have x of t input going into the system with a negative feedback, not a positive feedback, and the delay box and the integrator are here. Okay, the integrator of the system, and then you have the core also on the feedback line. Okay, so the two differences are that we are adding and then we are delaying the system on the feedback line. Now if I say D is equal to 0, I mean that the delay box has held nothing in it. Okay, so if this is y of n, and this is going to be y of n minus 1, it means that y of n minus 1 is 0. So therefore, my initial condition is 0. Okay, so to indicate the initial condition, I just use that notation, the delay box notation. Okay, but to go into the polynomial representation with operators, then I call this R, this operator R. Okay, so I replace the D with R. What do I have here is x of n plus p times D operated on n plus R operated on y of n gives me y of n. Okay? Now the D box is just a box, but R is the operator. R is the one that operates on this and delays it one time back. Okay? So I indicate the delay box as a tool to show my initial condition, but R is my real operator. Okay? So I do the algebra now equals y of n minus p r y of n. Okay? And then I put this in parentheses, y of n, 1 minus pr. And then output to input relationship becomes 1 over 1 minus pr. And the next step, just like I introduced the integral as an accumulated operator, or as one of this, in the complex domain, I replace R with 1 over Z, which gives me the Z transform. Okay? Then I can do the synthetic division, and I get 1 plus p r plus p squared r squared plus plus p to the n r to the n, all the way to infinity. Okay? So this thing, 1 over 1 minus p r is equal to that thing. Okay? And I know that 1 p squared p to the third p to the n is a sequence not added but numbers next to each other, the outputs of the system. This is G of n, which is the unit impulse response. Okay? And I see that these are G of 0 plus G of 1 times G of 1 times R plus G over 2 times R squared plus whatever. Okay? So this is actually summation of G of n times R to the minus n. R to the n. So therefore this is equal to G of n times Z to the minus n. And that is the G of Z, the Z transform of the system. Now you know this, you should know this, you should have studied the Z transform some. Okay, now moving on from this, if I want to introduce a second order system, what I do is the following. I put X of n here and get Y of n. Now remember, notice that I P1 here now, not just P. Because second order system, I'm going to have two poles. Okay? Two poles of the system. Alright? You sleeping? Alright, you have just 10 more, 8 more minutes. So now what I do is I take that Y of n, okay, call it Y1 of n, and then I use that as an input to Y2 of n. And I repeat the same thing R with a second pole, P2. Okay? Now what we have, therefore is the following. Y1 of n is equal to 1 minus 1 over 1 minus P1R times X of n. Okay? And Y2 of n is equal to 1 over 1 minus P2R Y1 of n. Just the same thing. Alright? So if I replace the intermediate variable y1 of n from this equation, okay, I get y2 of n equals 1 over 1 minus p2r times y1 of n, which is this, 1 over 1 minus p1r x of n. Okay? So my transfer function turns out to be 1 over 1 minus p2r times 1 minus p1r. Okay? So the more systems I add next to each other, the higher my system becomes. Of course, we're not going to do third order systems or anything like that in this class, so we're going to be left with this. How much time?
3 minutes.
3 minutes. You can win a battle in 3 minutes. Has anybody heard of Jean Sobieski? Polish general? Kara Mustafa Pasha? Anybody heard of Kara Mustafa Pasha? Merciful Kara Mustafa Pasha. No? You did?
Yes.
Unbelievable. Are you from Merciful?
No, but I live there.
You live there? Excellent. So is that 1960 anything mean anything to you? No. The second Vienna. The second Vienna assault of the Ottoman Empire. Right? Vienna is where Europe starts here. So the Ottomans were going into Europe. Vienna was the last castle, and then they were the second attempt. The first time was in 15-something colony, and now the second Vienna. What is that? Siege. Siege. Excellent. Aferin lan sana. Vallahi sende iş var ha. Tarihçi olacaksın. Sen yanlış okuyorsun. The second siege, Ottomans are ready. Alright? Everything is now, I mean, the Viennese are panicking and everything is like in Vienna, everything is burning. They are extremely hungry because of the siege, long time and everything. About to surrender to the Ottomans. In 3 minutes, Jean Sobieski comes down on the Ottoman armies in front of the gates of Vienna. Flank attack, flank means flank attack, destroys. 3 minutes. It all took the Ottoman army to be destroyed in 3 minutes. So that's what I just wasted here. So you have to give me 5 more minutes. Thank you. Alright. Believe me, I have more things to do than you. So the best example of this, alright, is the Fibonacci system. Has anyone heard of Fibonacci? You did. Unbelievable. She also did, but you did?
Yeah.
Unbelievable. Fibonacci, the model of Fibonacci, almost exclusively models everything, all the patterns that you see in nature, which are in a spiral mode. Alright, like the snail or the tornado or anything like that. Beautiful pattern. But we use the rabbit reproduction model to teach students, just like Dennis Freeman, our master. So imagine that you have a second order system, rabbits, okay? One pair of adult rabbits. Okay? One is male and one is female.
X, XY,
Huh?
male, female, XY.
Thank you, but rabbits, adult rabbits. So what we have is, let's say, one baby rabbit. Okay? The baby rabbit in the second cycle becomes an adult. Okay? And the adult rabbit in the third cycle remains alive, but then makes a baby rabbit. It's a pair. Or is a pair, right? In the fourth cycle, this is R plus R, and this becomes R. Okay, adult. This grows up, becomes an adult. This stays alive and makes a baby pair. Okay? So it goes on and on like that. So 1, 1, 2, 3. Go down and multiply. Go down and grow up. Go down and stay alive, and go down and multiply. 1, 2, 3, 4, 5. So what's the pattern? 1 plus 2 is 3, 2 is 5. 5 plus 3 is 8. That's the Fibonacci pattern. Okay, so if you give 1 into the system and stop giving any more, so what's your input? 1 and 0, 0, 0. What's that? Impulse response represents the system. Okay? So that's the impulse response, impulse input, and this is the impulse response sequence. 1, 1, 2, 3, 5, 8, on and on. Okay? Now how do you show this system as a difference equation? Y of n at any time n being the number of the pairs, alright, is going to be equal to, here for example, RR plus R. Okay, so this is y of n minus 1, and this is y of n minus 2. Gives you y of n. Alright? What is this? Y of 3 r plus y of n minus 2 r. Okay? So the equation is described by this following x of n, the unit input, okay, plus y of n minus 1 plus y of n minus 2. Okay? And then you do it in the R form. Y of n equal x of n plus r operating on y of n and r squared operating on y of n. Because one r operates on y of n gives you this, another r operates on this gives you that. Right? Alright, so and x of n is 1, of course. So y of n has to be 1 over. Why don't you be 1 over? Be 1 over.
R equals
Yeah, this is x of. That's what it is. X of, right? Right. So these are x and x. Today I named all x. Y of n is equal to x of n times 1 plus r plus r squared. So y of n over x of n is equal to 1 plus r plus r squared. That's your second order system. And we're going to solve the roots of this second order system in the next week. Alright, so we're going to have continuous time systems, first and second order, discrete time systems, first and second order. Alright, we're going to go into the Z transform for first and second order systems and even more. Alright, so we're going to finish the Z transforms next week. So we're going to go into state frequency response. Okay? Signals and systems. So, your homework. Do this in its entirety. And then study that in its entirety. All of it. Well, thanks for listening. Go home. Goodbye.